Hi everybody, my name is Saji Vila. I'm a PhD student from the University of Lleida, and we are going to present our improvements in the field of cloud computing optimization problem, presenting our paper WPSP, a multi-correlated weighted policy for VM selection and migration for cloud computing. The presentation is split into next topics. First, introduction, where we will put you in a context for the problem we are trying to solve, our intentions about how to solve the problem in the proposal, the techniques developed and how they work in policies, the scenario we perform to test our techniques against other techniques in the experimentation, the results we obtain, and finally, our thoughts about the work. The scenario we present is a cloud environment formed by a data center with hosts connected to switch and interconnected virtual machines, VMs, allocated on those hosts. The resources provided by the host are assigned dynamically to the requirements of the VMs, in our case CPU and network. The problem we are solving is the saturation of host CPU. That is, when the requirements of the VMs surpass the capacities of their host, some VMs must be migrated to hosts that can afford them, although those migrations will spread VMs that were communicating locally. There are different policies that affect the performance of the data center, such that the initial allocation of the VMs at the startup, the host saturation policy, the turning on-off policy for load balancing, in our case is deactivated, and how the network is managed. The cases we focus and improve are the selection of the VMs on the host is marked as saturated, with our weighted Pearson selection policy, and the allocation of the VMs with the minimum migration group technique. WPSP technique is aware of CPU and network dynamic loads. Unlike other techniques focused only on CPU and the current values, WPSP prioritizes influential VMs with high CPU correlation and low network usage. As a complement, MDG VM allocation technique will try to minimize the dispersion of the VMs to far hosts. These objectives are achieved following the next proposals. First, we develop a new network module to CloudSim, the simulator we use to conduct experimentation. That allows us more control about how the data crosses the topology, what has allowed to obtain more metrics related to network plus other metrics not present in the original simulator. Then we focused on construction of the policies observing how the metrics behave when we perform specific migrations. As commented previously, CloudSim is able to simulate a cloud data center with an excellent work on CPU management and VM migrations, but with problems with network handling. We extend CloudSim to ease us the configuration of experiments, the network module, and new metrics and techniques. Focusing on this, we present WPSP, based on the Pearson correlation coefficient. This helps the technique to know the degree of causality between two time series, in our case the relation between each VM and their host. In the images, we can observe an example of the data used to obtain the correlation. For each VM, its CPU and network usage is compared with its host, obtaining a value between -1 and 1, where -1 indicates inverse correlation, 0 no correlation, and 1 direct correlation. Moreover, we normalize and sort the CPU and network load for each VM to obtain their influence. For each one, we obtain the accumulated usage in the last window period. In our case, is 6. Then, the normalized values are obtained applying the formula for each one. In the table, there are shown how the resources usage of a set of VMs are normalized. Finally, obtaining the HVAL value for each VM, showing us the balance between CPU and network usage and their capacity to saturate their host. The remaining weight value is set to 0.5 and can be modified if the resulting values are too much or not enough spread. The decision about which VM is migrated falls on this last step. The VMs that can be migrated must be under a specific threshold, being a guarantee of that moved VM has high CPU and low network influence. The image shows the H-bar position of each VM depending on the correlations and the normalizations of the CPU and network. As the previous table shown, VM0 is the best candidate to be migrated because it is the nearest H-bar without surpassing the threshold, in our case 0.65. The next flow diagram shows the general schema for the WPSP algorithm. First of all, the host saturation policy sends to the WPSP the host with the CPU issues. Then we enter on the main loop. The algorithm will move VMs until the host becomes stable. To decide which VM will be moved each time, we must calculate its H-bar values, including the correlation and normalization for each VM in the host. The VM with the highest value lower than the threshold will be the selected VM. Finally, we will return to the starting point to check if the host is still saturated. Now, we know which VM must be migrated. Minimum distance group algorithm is in charge of deciding which is the destination host for each one. Hosts are clustered and ordered in ascending order by relative distance to the origin host. The host with less energy increment after allocate the VM from the distance group is selected. If no host can allocate the VM, the next nearest group is tested. If no host in the data center can allocate the VM, the migration is not performed. On explaining our algorithms, we present the other algorithms and the scenario we perform for the experimentation. The next VM selection policies are used to compare with WPSP. They are the default techniques that come with CloudSIM. Random search simply selects an arbitrary VM. Minimum migration time prioritizes VMs with few RAM. Minimum utilization selects the VM with less CPU usage. And finally, maximum correlation applies a linear regression to the last 12 samples and selects the VM with the most correlated CPU in relation to the rest of the VMs. The VM allocation technique also comes with CloudSIM, applying the interquality range in the last 12 samples to obtain the affordable upper threshold. If the current utilization surpasses this threshold, the host is marked as saturated. Finally, when a VM is migrated, the host that can allocate the VM and it has the best energetic performance is selected. The next tables show the VMs, hosts, traces, and network interactions you use to configure the experiment. The environment is heterogeneous to demonstrate our techniques work independently of the circumstances. CPU and network traces are equivalent to real ones. Following with the environment, the topology used is a tree shape with 16 switches, the red squares, and 36 hosts, the green circles. Further configurations are analyzed in the paper. As an example, here we can see in another data center how the communications between VMs, the clustered colored circles, are spread from the start of the simulation to the end. It is recommendable to maintain the VMs in the same host if it is possible to avoid intercommunications and link saturations. Before the experimentation, it is important to comment how WPSP is tuned. There are two main parameters besides width, that is set to 0.5 as explained previously. Window is a number of samples used to calculate the Pearson correlation and normalized values. In the image, we tune the window value from 2 to 30. We decided that the number between 6 and 12 offer good results. With numbers lower than 6, we obtain extreme values. On the other side, over 12, there is no improvement, and at the end, most of the values fall near 0.5. In the experimentation, we use 6. The other parameter is edge limit, set to 0.65 as shown in the algorithm section. This is a parameter that must be tuned depending on the CPU and network usage of the data center. In this case, we selected 0.65 after the drop of unassigned MIPS. The number of migrations grow linearly and the saturated data has not an important growth, so the best value according to the used metrics is 0.65. For the results section, we focus the comparison using a set of metrics obtained from the simulation. First, we present some highlights about how the combination of our techniques have a better performance. Then, a general comparative using or not MDG, and finally another comparative with all the tested metrics, showing the improvement in all of them. Starting with the user bandwidth, it can be appreciated that our techniques have a high dispersion, even though our worst solution is better than the best from the others, obtaining a mean improvement of 5%. About saturated data, that is the quantity of megabits that the communication links have not been able to serve, our dispersion is similar to the others, and the improvement is substantially better, at 16% in relation to the second best technique, MMT. Continuing with the CPU consumption, there is not a big gap about saturated hosts, between 9 and 11% of improvement. However, saturation only indicates that the hosts are over 70% of its capacity, so it is correct that the technique tries to concentrate resources in less hosts. The event that really is harmful is the oversaturation, where a host cannot afford the MIPS required by its VMs. In this case, our algorithm reduces this issue in a 40% in relation to the second best techniques, MMT. The most important metric, where WPSP shines, is the number of migrations, reducing in 89% the number of migrations on average. This demonstrates that WPSP migrates the most influential VMs, who really are provoking the CPU saturations. Moreover, the migrated VMs have a low impact on network, and if it is not enough, MDG will move the VMs to near hosts to avoid dispersion. Focusing only on MDG, it can be appreciated that independently of the VM selection policy, the technique improves all the metrics, some in a slightly way, where MDG is around 4% better than the default technique, others like unsatisfied hosts around 13%, and finally in a significant way, like the quantity of data moved due to the migrations, ramming bandwidth, where MDG is around 44% better than the default technique. In the last comparative, we showed the percentage of improvement of our techniques over the other ones. In the one hand, we obtain the benefits of the WPSP due to its accurate selection of VMs, affecting directly on the number of migrations, performing more MIPS due to VMs are not migrating or they are placed in better hosts. Furthermore, WPSP does not encourage migrations of VMs with high internal communications, reducing the external traffic and hence the data saturation, obtaining an improvement of 20% in average. On the other hand, unrelated with network, VMs with important internal communications will be migrated to near hosts thanks to MDG, reducing in 89% in average the quantity of data related to migrations. After showing the results, we can conclude MDG performs better VM allocations in relation to the default VM allocation technique from CloudSIM. WPSP selects correctly the most influential VMs, reducing host saturation, unsatisfied MIPS, and the dispersion of the VMs, and in combination with MDG, reducing the traffic in the data center. To conclude, among general improvements in the rest of metrics, we would like to highlight 51% less unsatisfied hosts, 20% less traffic, and 89% less migrations. The methodology used can be improved with alternative parameter tunings, topologies, and implementing more techniques. Currently, the migration cost is not penalized, so it could be interesting to apply it from a real environment to obtain more realistic results. Finally, we can continue developing techniques, for example, using other kind of correlations like Spearman and Kendall. Thank you for your time, and we hope this work can help you in your research.